Hey, good afternoon, everybody. It's Michael McClellan. Welcome to another L3 webinar. A couple of housekeeping items before we introduce Mike and Terry. This is a go-to webinar, so your phones are actually muted, which is good and bad. The good part is we don't have to worry about dogs in the background or angry wives. So anyway, if you guys want to ask questions, there's a question box up to the right on your screen with a question mark, and we'd love for you to ask questions. And if a few of you want to go ahead and test that, that'd be as well. There are a few handouts attached to the presentation. You'll also find those to the right side of the screen. And a certificate will be emailed out tomorrow around 4 or 5 p.m. And if you do not receive a continuing education certificate by then, please email us or call. And now I'm going to turn it over to Mike Ramalachan and Terry Smith. Both of these guys are with GE Multilin.
Hey, good afternoon, everybody. This is Mike Ramalachan, GE Grid Solutions. I'm the lead application sales specialist here at Grid Solutions, specifically dealing with protection and control and automation, application support or pre-sales, post-sales support. Terry's also on the line, and he's my superior, so to speak. And today, hopefully, we will introduce you to the topic of bus protection for today's seminar. We're going to attempt to present the topics for the next hour or so and take questions as time permits. So as Mike said, please type your questions in the question box, and as we go through, me or Terry will answer those questions. Today's discussion, as I said, will focus on the bus protection, and we will talk about protection techniques and schemes and how those are affected by various power system conditions such as CT saturation issues. So before we get started, just if you need to contact us, so as I said, Mike, Terry and myself are on their email addresses, phone number. This will be in the handout that Mike mentioned. So Eduardo is our regional sales manager here in the Southeast. I'm located in Orlando, Florida. Terry's in Tennessee. So today's agendas, as we'll go through a brief introduction of bus protection. We won't have time, and the time is really not enough to go into a lot of the details in setting and calculating bus differential settings. So most of the discussion will focus more on the protection techniques, bus arrangement and components within a bus, some CT saturation on how those affect bus protection, and some advanced algorithms for handling CT saturation. So let's go into an introduction to bus protection. So firstly, what are the challenges that we face when it comes to protecting a bus zone? As we know, a bus is a junction point where sources terminate, typically in our transmission, where our transmission and distribution lines terminate. And then we have feeders, radial or otherwise, from those bus zones. So if a short circuit occurs on the bus, there will be multiple sources contributing to that fault circuit current, resulting in very high levels of fault current. This can result to damage to the equipment from mechanical stress on the bus bar, which can lead to CT saturation if your CTs are not sized properly, and even if they're sized properly, due to DC offset issues, you could still saturate your CTs. And it can be a safety hazard to personnel due to the high level of arc flash energy produced. Last week, we went through an arc flash seminar, so we introduced the concept of arc flash and some of the techniques that we use to mitigate arc flash, and bus differential that we're going to talk about specifically today is one of the techniques that we discussed when we talked about arc flash mitigation. So because of all these issues, we need to identify and isolate these faults to minimize their effect on the power system. Conversely, maloperation of the bus protection system has significant impact to us because we can unnecessarily take out customers, downtime for our processes, which can have significant financial impacts, and can cause voltage stability levels, which can adversely affect equipment outside the bus zone. And it can lead to widespread system collapse. And the one I always think about is the 2003 Northeast blackout, because I was in New York City at the time. It was a very hot summer day. And I had to get home on the subway. The subway wasn't even running. I had to walk home that day in the hot summer heat. Had to cross over the bridge. First time I've ever walked over the Brooklyn Bridge. So it was not a very good experience. And we know that collapsed, ranged all the way from Canada all the way down to the south. Therefore, we must design a dependable and secure bus protection scheme. Dependable in that it should operate for bus fault within its zone and in minimum time, and secure in that it should only operate for faults on the bus. Obviously, maloperation, we don't want the bus zone to operate for faults outside of its zone because of all the issues that I just discussed. It is not always easy, since to enhance one, it will affect the other adversely. Example, increasing dependability can affect security, or increased security can affect dependability. For the most part, we try to err on the side of security because of the criticality of the bus to the switching of power. There are many different bus topologies. We're going to go through some of the most typical ones today. We'll go through some of the CT placements for those bus topologies. And one thing we're also going to talk about is bus reconfiguration, in that there are different apparatus, specifically breakers and sources and feeders and transformers, that will be connected to different parts of the bus at different operating times. And we need to deal with those reconfiguration issues when we're talking about bus protection. The switching can happen in any number of ways, manually or automatically. Obviously, automatically gives us the most flexibility, though we don't have to worry about anything as we're doing switching. Manually, you have to follow some sort of procedure to be able to, when you're doing bus reconfiguration, to be able to follow your procedures properly and have procedures in place. So high-speed bus protection advantages. When we talk about high-speed tripping, we're talking about tripping in about a cycle, so about 12 to 24 milliseconds, so cycle and a half. High-speed tripping is advantageous in that it can reduce arc flash energy and minimize equipment damage. So, for example, saving a transformer versus replacing it, being able to repair it on site versus completely taking it out and replacing it. The cool thing about bus protection, it has no impact on system coordination. Coordination can add significant tripping time, as much as a couple hundred milliseconds to several hundred milliseconds. So that can cause a lot of arc flash energy, can cause a lot of equipment damage if we're relying solely on coordination. So bus protection does not affect coordination, has no impact on coordination. It operates independent of coordination. Bus protection is always in operation. So, for example, like if you have an arc flash issue and you need to take care of that arc flash issue, some of the techniques that we talked about last week is applying a mechanical maintenance switch or a push button to put the relay into arc flash mode or fast overcurrent mode. With bus protection, it's always in operation. You don't need to put it in arc flash mode. It's always in operation. So you don't need someone to turn something on and off. You don't need to have procedures in place to be able to do that. It's always on. And minimizing damage leads to shorter repair times and less downtimes, obviously. So some of the typical bus arrangements that we'll see when we look at buses. The most simplest one is the single bus, single breaker configuration. This is mostly distribution, industrial levels, so lower levels, not necessarily lower voltages, but a lower distribution industrial level. It offers no operational flexibility here. If you need to do maintenance on the bus, you need to take all these feeders out of service, all your sources out of service, all your loads out of service. If you need to do maintenance on a breaker, there's no way to switch that load onto an adjacent breaker to be able to carry that load very quickly. You have to do switching downstream to switch your load on the low voltage side. Fault on the bus will take out the entire circuit. So fault on the bus will take out all your sources and all your loads. So you basically will lose your entire plant or bus section or loads or whatever that those are feeding. So building upon the single bus is the multiple bus section, which we call a single breaker with bus tie. And you guys are probably familiar with this a lot in the industrial application, which we refer to as main tie main scheme. And with this scheme, it offers limited operational flexibility, more flexibility than the single bus, because you can have multiple sources here. And maintenance on one bus, you can still maintain loads on bus number 2, certain number of loads on bus number 2. Typically, you would have a source feeding into bus zone 1 and bus zone 2. You could operate that tiebreaker normally open and normally closed. So if you lose a source, if it's normally closed, you will be able to pick up the loads in the adjacent section if you lose the source on that section. If it's normally open, you can have a main time main transfer scheme where you can then pick up the loads that from the source that is lost by the adjacent source. So it offers a little more flexibility than the single bus configuration. We then already build upon the multiple bus section configuration. We go to what we call the main and transfer bus. So we have what we call a dedicated transfer bus, and that transfer bus is connected to our feeders, load sources by an isolator switch. And the isolator switches are then connected to our main bus and through our breaker. So what this helps us to do is increases operational flexibility. If we need to take an outage on the bus, we can switch over to the transfer bus temporarily. If we need to take an outage on a breaker, we can basically feed that load through the transfer bus. So for example, in this case, if the leftmost breaker, if I wanted to take that out of service to maintenance, what I would do is I would close the disconnect switch in the transfer bus. I would close this tie breaker in the middle so I could pick up that load from the transfer bus. Then I would open to do the 2 disconnect switches on that breaker, and then I'll be able to then start doing work in that breaker. So it gives me tremendous flexibility for maintenance. And if I have a fault on the bus, even though I'll trip the bus, I'll lose my loads temporarily, I can always transfer over to the transfer bus, pick up my loads fairly quickly. And again, building upon that is the double bus, single breaker with bus tie. This is very common in the West Coast. It mostly at transmission and distribution levels. You're not going to see too much at industrial level. The flexibility of this, you could do maintenance on breaker maintenance without the circuit removal. So you open the disconnect switches and you close the disconnector to bypass that breaker. Then you could draw that breaker out and do some maintenance on it. And fault and a bus disconnect only the circuits affects only the circuits on that bus. So if I have a fault on bus zone 1, it's only going to affect the loads that are connected to bus zone 1. I could quickly transfer those loads over to bus zone 2 by opening and closing those disconnect switches. Now, the problem with this scheme is it's a bit more complicated for a burst relay, because depending on what position these disconnect switches are in, it could be either part of bus zone 1 or part of bus zone 2. So our differential protection will have to be dynamic in that it has to, based on the position of the isolator switch, the disconnect switch, it'll then decide which zone that feeder or CT is connected to and make the appropriate decision when it needs to trip and when it needs to create the differential currents for the algorithm. And we'll talk about dynamic bus replica a little bit more later. Then we have mostly at the transmission level or high voltage or extra high voltage levels, is the ring bus arrangement. It offers high operational flexibility with the minimum number of breakers. So in this case, if I wanted to take an outage on line 1, I could then open breaker B1 and TB1, isolate line 1, and still have the other lines in service. I can then isolate line 1 if I wanted to. If there was a disconnect switch on the line side of line 1, I can then open that disconnect switch, close the 2 breakers, maintain the ring back together. So if there is a fault in one of the bus sections, it only affects that bus section. All of the other bus sections are still in service and are unaffected. In this scheme, typically you might not have a dedicated bus protection for each section. What you might do is you might incorporating the bus protection within the protection that's covering the line. So the line protection might be covering the bus. Some cases you might have a dedicated bus protection also, but then in that case, you will need a CT on the line side. A lot of cases we don't have a CT on the line side, so we incorporate the bus protection in the line protection. Please ask questions. I'm not seeing any questions. Please ask questions as you think about them, and we'll try to answer them. And the other arrangement is the breaker and a half bus. And the reason it's called breaker and a half is, as you could see on each section, there's 3 breakers and there's 2 feeders. It could be source, it could be load. So because of that, 3 breakers to 2 sources or loads, that's where the breaker, 3 divided by 2, that's where the breaker and a half acronym comes from. This type of configuration offers a lot of operational flexibility here, uses most often at higher voltage level. And the reason is because of the cost, requires more breakers, obviously. You could see for every 2 source or load sections, you need 3 breakers. The middle bus sections are covered, again, like the ring bus, are covered by the line protection. There's not a dedicated bus differential relay there. However, these, what we call the synchronizing buses, the bus zone 1 and bus zone 2, they have a dedicated bus protection relay. But if one of those there's a fault in one of those bus, we basically open the breakers associated with that bus zone. In this case, the breakers covered by the red lines for bus zone 1, and it has no effect on our sources or loads because bus zone 2 is still in service and is carrying whatever switching loads that goes through from the various sources to the load. So nothing is affected. So this is what we refer to as an N-1 contingency, where one failure will not take out any part of our system. So let's talk about some of the protection techniques that we use when we talk about bus protection. Just as a reminder for everybody, the bus protection essentially operates based on Kirchhoff's current law. And what that law basically says is the sum of all currents entering the node must equal 0, or the currents entering the node must equal the currents leaving the node. So that's where the differential phrase comes from. So we're doing a differential calculation, a subtraction. So currents entering the zone, currents leaving the zone, we do a subtraction between the two, and they should basically be zero or close to zero. Obviously, there's other factors like CT inaccuracies and CT saturation issues that we're going to talk about in a little bit. The variation is in how we implement a bus protection scheme. There are various existing implementation that we will talk about in more detail. So the more common ones that we'll be discussing today is the unrestrained differential, the interlocking blocking scheme, or zone interlocking blocking scheme that you might have heard of it, high impedance differential, and low impedance differential schemes. So before we start talking about these schemes, Mike is going to post the poll up. Mike, are you there? Mike? Okay, so he started the poll. So the poll is, if you can give us an idea of, what kind of bus protection scheme do you specify or you use within your facility? The options are going to be what we talked about: the unrestrained, interlocking, high impedance, low impedance. Or if you don't use none, then include that in the poll. So we get an idea of the audiences, what do you guys use and what do you specify. But we will talk about more in detail. Don't worry about if you don't know what these schemes are or what they mean and how they're implemented. We will get into them in more detail. We will do that as soon as the poll is closed. How do I know when the poll is closed? Okay, here's the timer. Sorry about that. So we have about 60 seconds in that poll, so let's move forward. So let's talk about the first one, and that. So if you've selected the unrestrained differential, or commonly referred to as the overcurrent differential scheme, then you're probably familiar with a lot of these. Oops, why is it not in presentation? Sorry. So typically a differential current is, as we mentioned, created externally. For this scheme, the differential is created externally to a current sensor by summing all of the current CTs. So the current sensor being the relay. Obviously, when you're paralleling CTs, you're going to have to match the CT ratios. So CT ratio matching is required. If the CT ratios don't match, you might have to add auxiliary CTs to the circuit to be able to match the CTs. The disadvantages of using this scheme is external faults can cause CT saturation, leading to spurious differential currents, and not even CT saturation issues, but inaccuracies in CTs can cause spurious differential currents. Transient during when you first strike the fault is an asymmetrical transient, because the CTs are not going to perform the same at the exact moment in time. They're going to perform a little bit in a variation when you first strike that fault. So you will have spurious differential in that part of when you first strike the fault, or when you start to when the CT start to saturate. So to cope with these effects, what we usually do is we add an intentional time delay to cope with those effects. To cope with effects of like inaccuracies in the CT, what we do is we might increase the minimum pickup of the overcurrent element, so we desensitize the element. So those are the two advantages to using this scheme. Is you're going to have an unnecessary time delay to scope with these, and you might have your pickup might be set a bit high, and hopefully it should be able to still be able to protect for any type of bus fault. But if you have like a high impedance bus fault, it might not be able to, depending on the sensitivity set. So the unrestrained differential function can be used in microprocessor-based protections. In microprocessor-based protection, we don't typically use the overcurrent by itself. We could use it as a check zone to a main differential. Typically, this is used in some older designs you might typically see these with an overcurrent electromechanical relay, and then when you upgrade, you might have no choice to upgrade it because you don't want to change all your CTs, all your CT connections, because we're going to talk about for the other schemes, you will need to change your CT connections to be able to move from a overcurrent differential to, for example, a low impedance bus differential. A simple protection for distribution busbar can be accomplished in an interlocking scheme, which is building upon the overcurrent scheme. So the overcurrent relays are placed in an incoming circuit and all the outgoing feeders. The feeder overcurrents are set to sense the faults on the feeders. The overcurrent in the incoming circuit is set to trip the busbar unless blocked by any of the feeder overcurrent relays. A short coordination time delay is typically required because you need to wait for that blocking signal to come in. Typically, how this is implemented using electromechanical relays or your typical conventional scheme, even with microprocessor relays, we would wire this blocking signal from the feeder overcurrent relays to the incoming overcurrent relay. So you need a wiring from all of those devices going back to the main incoming relay. But however, with all modern microprocessor relays with communication capability, and all our relays, our 8 series has up to 2 communication ports. So UR has up to 3 communication ports. It can come in a number of options, either RJ45, fiber optic options. So instead of using hard wiring and having to run all that wiring back to the source relay, what you could do is just connect a fiber to a switch or an RJ45 to a switch and use the communication via goose messaging, 61850 goose messaging, to be able to send that blocking signal to the source relay to get that blocking signal. And it's as fast as if you're using a wired scheme, even so you're not sacrificing any time within the scheme because you still have to wait a little bit to allow that blocking signal to come in. So there's a little bit delay there. So it can reduce your arc flash time from a couple hundred milliseconds, like 200 to 300 milliseconds, down all the way to 40 to 50 milliseconds. So it's a significant, almost more than 1/4 saving in this operation time, and that can be significant for arc flash energy. The other advantages of using the COM scheme versus the hardwire is the hardwire scheme is if there is an issue with your wiring. So for example, there's a ground, water fell into the panel, and this happens all the time. I used to work for the utility in New York City. So we would have all sorts of grounding issues during snowstorms. And not during the snowstorm when actually the snow starts to melt, because then it starts to melt, the water gets into the cable. There might be some break in the insulation, some degradation in the insulation, and then you would have a fault, you will have an issue. You could have a maloperation because you have these grounds. You might have a relay failing to operate because you're not getting the signal to where it needs to get to. And when you go to test it, the water has dried up now. It's gone because when you're testing it, you're not testing it in the middle of a snowstorm or when the snow is melting. You're testing it on a clear day. So the issue is gone. So it's impossible to troubleshoot and find where the issue is. So not only that, you don't know about the issue until something happens, right? So you have a maloperation or you have a failure to operate. With the communication scheme, it's constantly monitored via communication. Ethernet communication, one of the things with Ethernet communication, it's monitored all the time. If there's an issue with the Ethernet communication, either the relay will alarm saying, hey, I'm not getting this I'm not getting signal from the downstream relays, or the switch will go into alarm, say, hey, this port connected to this relay, I'm not seeing any traffic on it, or there's some issue here. So your circuit is monitored in real time, so you'll know about it before it's too late. It's easy to apply. So as I said, any modern microprocessor relay has the capability, Ethernet communication capability. So if you have relays already installed with communication capability, by just adding a couple of switches and a couple of fiber optic or RJ45 connections, some configure 61850 configuration to send the blocking signal and receive the blocking signal, you can easily implement this scheme. And it's very economical. As I said, there's not a lot of hard wiring used. You just need the comms cable, which you probably already have for if it's a newer upgrade to a microprocessor relay. But it is limited to simple bus bar protection like this, where you just have one source coming in and then all of the other devices are radial feeds. The problem comes in if you have multiple sources and or you have a generator or something in one of these, it's not a radial feed, it's a source, then this scheme falls apart a bit because now currents can go in either direction, right? So if you have a fault, an external fault, if you have on the right feeder and there was a source, a generator, say on the left feeder, you would have fault current coming not only from the transformer source, but from the generator source. So that generator relay would send a blocking signal to say, hey, there's a fault within this zone, you should not operate. That's okay if an external fault, but if it's a bus fault, then it's going to block the bus fault from operating. So it falls apart if all your if there's any sources other than your main source. The other technique that we use is the high impedance differential, or referred to as over voltage typically. This technique has been used for a long time, so a lot of legacy bus bar protection you will see have some sort of high impedance differential relays, electromechanical high impedance relay. Similar to the overcurrent in terms of the connection of the scheme, where all the CTs are parallel by connecting the secondaries in parallel. With this, however, you do not want to add auxiliary CTs or any other devices within the high impedance scheme, except for the high impedance relay and maybe a stabilizing resistor, which I'll talk about, because burden is very important to the scheme. Calculations that you use to develop the pickups and settings for these schemes are based on burdens of the CT. So one of the disadvantages of using the schemes is that you need dedicated CT. You must have dedicated CT. So these CTs cannot be used for anything. It can be used for overcurrent backup, can be used for breaker failure, can be used for auto reclose, and they have to be the ratios have to match. So this scheme can be a little bit difficult to implement in terms of if you have a transformer in the zone, or in our discussion, we're talking about bus zones, so it's pretty easy. You can have all the CTs in the same ratio. But when you're talking about protecting a transformer for a high impedance differential, you also have to take into account the winding ratio of the transformer. Typically, the relay used is an over voltage relay for some of the more legacy designs. But into most of today's design, you can use an overcurrent relay, or really technically any overcurrent relay that have the sensitivity and the speed to be able to implement this scheme. One of how the scheme basically operates is it's using the same principle, right? Current in equals current out. So if you have external loads or external fault, basically the currents will circulate within the CT circuit. So for example, I1 is coming out of the bus, I2 is coming into the bus, I3 is going out, and IN is coming in. So basically these currents will be differentially equal to 0 when you add them up. So they will circulate within the CT circuit and they will not go into the relay. So the differential current in the relay will be 0, and hence the voltage across that relay coil will be 0. So the relay will not operate for any type of external or conditions with normal loading or an external fault. However, this scheme, when you have CT saturation, it can deal with CT saturation by the sensitivity of the setting that we put into the relay. And how we do that is we take a CT, the worst case CT, and we say, what if the CT completely saturates for an external fault? And then we do a calculation based on the burden of the wiring, the relay, and all the things in your circuit. We do a calculation to determine if that CT is completely saturated, what type of voltage will develop across that relay. And then we set our pickup above that, because we know if we have an internal fault, it's going to be above that pickup. But for an extremely saturated CT, we don't want to operate. So it's a very secure scheme against CT saturation, built-in secure scheme against CT saturation. This principle has been used for a long time, over half a century probably, even more, because of it's robust, secure, and fast. Talking about cycle to two cycle operation time. So some of the advantages and disadvantages of using the high impedance scheme. The advantages, as I mentioned, is fast, secure, and proven. It's a very economical scheme in the sense that all you need is one relay. That junction point I talked about where the CTs are parallel together, this can be in the yard somewhere. This does not have to be in the control room. This could be in the yard somewhere. So you don't have to bring all of these CTs to one location. They can be junctioned anywhere in the yard or anywhere in your switchgear. And then the result, just 2 wires, can come back into the relay. So you don't have to run a lot of CT wiring. So it can be economical, and it just requires a simple over voltage or over current relay. It does require some calculations that I talked about in terms of how do you set the pickup. Can apply to small or large buses. It doesn't matter. It can high voltage, low voltage. Can apply to any time of bus. However, the disadvantage, as I mentioned, it does require dedicated CTs with the same CT ratio. It cannot handle nicely inputs from CTs set at different taps. So if you have multi-tap CTs, we usually recommend set at the maximum tap, at full tap setting, because if you set it at tap positions, you are reducing the burden and the electromechanical characteristics of the CT, and that can affect the scheme. Depending on if it's external, internal fault, you will have to provide adequate settings for sensitivity and security. And as I mentioned, usually how we do is we saturate one of the CT, and we then, based on the burden calculations, we come up with that number. So to be able to get the scheme, to be able to get it and calculate the settings, you do need to know a number of things about the circuit, specifically the burden and of the circuit and the performance of your CTs. So things that might not be available during the design stage or during the setting stage. So it can be sometimes, if you don't have that information, it's easy to set once you have that information. But if you don't have that information, then you might have to make some judgments into the setting.
Hey, Mike, can I ask you a question?
Sure.
The way Multilin does it, we typically use a 2000 ohm resistor. And we recommend a C200 minimum for bus differential, which gives us 100 milliamps of current. And that's what we actually monitor.
Right. So basically, it's the minimum you want a relay class CT of C200 for any type, but that's the minimum requirements for relay. I was going to talk about the HID module a bit on the next slide,
Okay.
To talk about the stabilizing external resistor also. So just give me 1 second and we'll get to that slide.
Okay, great.
just to finish off on this slide in terms of the disadvantages, as John just mentioned, it does, in addition to a stabilizing resistor, and we'll talk about the stabilizing resistor next, we might require a voltage limiting varistor or non-relay linear resistor. And that's because, remember I mentioned, this is a voltage that's developed. So if you have a high internal fault current, all that fault current is going to go through the relay, and that will develop a high voltage across the relay coil, which it's probably not going to be rated for. It could be in thousands of volts. So to be able to deal with that so that we don't damage the relay coil, what we do is we put that varistor across the relay coil so that when it gets to a certain voltage level, we basically create a short path, a path to ground for that voltage, to reduce that voltage or keep it within nominal ranges that the relay can handle. So we do need, in addition to the stabilizing resistor, we might also need a voltage limiting varistor. The disadvantages, it does not provide the benefits that come from a microprocessor relay. For example, metering. You cannot meter off of this because you don't know the individual CT metering. Oscillography, it's not going to help you much. You can't do break of failure using the same CTs in the same relay because you're not reading the current for the individual feeders. All of the metering, monitoring data is not available anymore. So a lot of the benefits that come with a microprocessor relay, you're not going to get if you use a high impedance bus protection scheme. So as John mentioned, with the high impedance scheme, there's a couple of things that need to come up in the design, and one is what we refer to as a stabilizing resistor, which is in series with the overcurrent coil. So this is an example, an HID module containing the stabilizing resistor and the varistor, that voltage reducing resistor or nonlinear resistor, to keep it within the voltage limits. This is kind of a drawing, typical connection drawing of the high impedance scheme. You could see the resistor and the varistor there. And there's two ways of determining that resistor. You can have a variable resistor or you can have a fixed resistor. With the fixed resistor, and the HID module has a fixed resistor value, as John mentioned, with that fixed resistance, you can only have certain sensitivity levels, and that's what John mentioned. It could be up to 100 milliamps or lower than that. So there's a sensitivity of range that resistor gives you. The other option is you can have a variable resistor, and you basically, with the variable resistor, you need to know all the details of your short circuit, your CT burden, CT performance, and you can calculate what we call the stabilizing voltage, meaning the voltage that will be impressed upon the high impedance coil when the CT completely saturates. Once you get that stabilizing voltage, you can calculate what that stabilizing resistor is, and you could select a value. We could do both options. We could do the fixed in the HID module. The advantage of the HID module is you don't have to worry about selecting a resistor. You don't have to worry about mounting that resistor. It comes all enclosed in that box. But so the only thing you need to do is make sure the sensitivity and such using that resistor is what you're going to get. And for most applications, that fixed resistor is not going to be a problem if you use it with one of our relays. If you use it with a different relay that might have a different sensitivity range, then the sensitivity range changes. However, we do have both options. I did not show the options of the option for the variable stabilizing resistor because I don't think that's so much used in the industrial application. Probably if you're going to use it in industrial application for simplicity, the HID module is the best bet to go. So the kind of running a little bit behind time, sorry. So the last scheme that we introduced that we're going to talk about is called a low impedance differential. What the relay does, it's a percent differential relay, creates a restraining signal in addition to the differential signal and apply the percent characteristics or restraint characteristics. So this could be referred to as low impedance, percent characteristic differential, percent differential, restraint differential, all of those terms you can refer to it as basically the same scheme. And it uses a differential principle, again, current in equals current out, and it also calculates a restraint quantity. Then it calculates what percent of that differential to the restraint that I'm calculating, and if it's over a certain percent, then it's going to trip. So the settings that we set is the percent. How much percent of differential do we want compared to the restraint before we issue a trip? And that will depend on CT saturation. How much CT, if you don't have a lot of CT saturation, then you can set that slope fairly low. If you have a lot of CT saturation, then you have to set that slope pretty high. Protection for reconfigurable buses becomes easier in this scheme because now you're reading the CTs from each individual feeder, and it can be accomplished without switching secondary CT circuits. So if you can like for the some of the bus topologies we talked about, when you're switching from one bus to the other, you don't have to go physically rewire your CT or have a switch to switch the CT over from one bus to the next. The relay can automatically do it internally if you tell it what the disconnector switch position is, and it will automatically switch that CT. This approach, unlike the high impedance, does not require dedicated CTs. And as with the high impedance, it can tolerate substantial CT saturation, provided it's set properly, and provide high speed tripping. Non-dedicated CT meaning I can use the CTs that I currently have on my feeders. So if I have a retrofit application, I don't necessarily have to go in and replace my CTs, well, depending on what side of the breaker those CTs are located. I don't necessarily have to go in and replace my CTs. I can use some of the existing CTs to implement a low impedance differential scheme. The disadvantages, of course, is the wiring. All of these CTs have to individually run to the relay. So it can be, and cost-wise too, it can be more costly to install it, right? Yeah, just kind of mentioning, what's the difference between the advantages and disadvantages of the low differential, low impedance versus the overcurrent scheme, as I mentioned. No dedicated CT, we can do CT compensation. It doesn't have to be the same ratio. We could do up to 32:1 compensation. We're going to talk about some advanced algorithms that we use for differential protection to take care of those CT saturation issues. The protection is reconfigurable very easily based on the bus replica. We can use it for multiple users. We could use it for breaker failure. We could use it for auto reclosing. We can reuse the same CT for different functions. You don't have to have a dedicated CT for every function like in the high impedance scheme. We can replace this is more on probably in the utility than so much on the industrial, but if you have long runs of CTs that if you need to implement the scheme and you need to run those CT wirings long distances, what we could do is we could do what we refer to distributed scheme or process bus scheme, where we can connect these CTs into a merging unit on the switchgear and run a fiber optic back to the relay. So that alleviates some of the CT burden issues and the number of runs that we need to do for those CTs. And remember, when we're running CT, we're talking about 10 gauge, 8 gauge thick cable, which is also difficult to work with. So replacing with fiber makes it more easy to work with and install also. Just some of the products that we have is a little bit of a commercial part of the presentation here is the B30, which we could do up to 6 for low impedance. We're talking about low impedance bus differential. We could do up to 6 circuits, up to 6 restraints in the B30. And then if you have more than that, we can go up to what we call is the B30 multi-box solution, where we can have up to 24 circuits in a 3 or 4 box solution. But again, you will need to have multiple boxes. And basically how this works is each box might do like a phase, A phase, B phase, C phase, 3 boxes, and then maybe a 4th box. If you have to do a bus replica, you need to have all the isolators, breaker statuses come into that box, and the relays will communicate those signals back and forth with each other. So we could up to 24 circuits in this this configuration. When we go to the digital solution, as I talked about before, when we use the convert the CTs to fiber, we could do up to 24 circuits also in a single box. Just a summary for the low impedance and the UR bus differential. It's a very excellent performance. We're talking about less than a cycle for operation plus contact operation. Very good stability for external fault. Straightforward to configure. The bus replica, we're running a little bit of time, but basically in this example here, I'm just showing you that we will have multiple buses. And based on the position of those isolator switch, that feeder might be connected to south bus, or it might be connected to the north bus. So the bus differential relay needs to know which bus it's connected to, so it includes or excludes that CT in the bus differential algorithm, and it trips the appropriate breaker. So we need to bring all of these isolators statuses into the relay, and the relay, based on those isolator statuses, it will switch the AC, the CT currents from north bus to south bus, and vice versa, but depending on the position. So what do we talk when we talk about a differential algorithm? When we develop a differential algorithm, what are the goals? Obviously, we want good response, right? We don't want it to operate for fast transients or anything like that. Fast operation time, low speed, subcycle, better. Good restraint techniques so that we can reduce or eliminate issues for CT saturation. And for providing dynamic bus replica, and all of our microprocessor bus differential relay have all of these capabilities. In addition to, we have an additional advanced algorithm for dealing with CT saturation. But before we talk about that for a bit, we wanted to just include this poll based on what we've talked about already about bus protection, and what we're going to talk about is, now that you have an idea of what bus protection is, you could talk to us about if you need help designing or looking at upgrading your differential, whether you want to look at low impedance versus high impedance. We can certainly talk about that, or any other questions you might have based on this seminar that you might not have asked in the questions that might come up later on. Just say yes, and we'll contact you to discuss any of those. So we got about 30 seconds if we could do. What we'll talk about next is some of the actual algorithm that we use to cope with CT saturation. And as I mentioned, CT saturation is an issue for any type of relay, because it's an issue because the CT is a magnetic core, right? So it's always going to be subjected to overfluxing, over its excitation. It's going to always be subjected to that CT saturation issue if it's pushed to its limit. It's been about a minute, so we'll close that poll. We'll move on. So what happens during an external fault when we're looking at a differential versus restraint curve? Remember, the differential, the low impedance relay calculates a differential and a restraint. So when we have an external fault, I should expect to see very low change in differential current, because current in still equals current out, right? But I should see a high increase in restraint, because remember, in in the restraint formulas that I provided, the restraint is usually the maximum current, or it could be the summation of all the current depending on the relay. When we do summation or maximum, we're talking about the magnitude, not with respect to phase. So if I have 1 per unit entering a zone, 1 per unit leaving a zone, the differential is 0. But if I'm using max restraint, the restraint is 1 per unit because the maximum of those two restraints. Or if I'm using the restraint added up, it will be 2 per unit depending on the type of relay. All our relays use the max restraint. I know some other vendors might use the total restraint. Whatever the case might be, that just affects how you set the slope setting. So for an external fault, what you'll see is normally you're operating at time t0, and then you'll see very little increasing differential, but a big increasing restraint. So we go from what we call from region 1 of the curve to region 2 of the curve. You can see where it has that higher slope. Now what happens if we have a CT saturation? As we strike an external fault, the CT for the first whatever quarter cycle for a certain time period, it will generate the primary current effectively until it starts to saturate. What happens when it starts to saturate? I'm going to see an increase in differential current without any significant increase in restraint current. So my change in differential will be overwhelm my change in restraint. So I can use this in my algorithm. I can use this trajectory to be able to determine if the CT is saturated or not. So basically, I know if I go from region 1 of the curve to region 2 of the curve, and then I go into the trip region here, then I know this is a CT saturation issue, and I need to do something about it. A couple of things that I could do. I can increase the delay, but we really don't want to do that. But what we typically do is we mess with the slope settings. And this is basically the typical settings of a differential. You'll have slope, you'll have pickup settings. Again, this you just don't have enough time to go through how do we determine all of these values. So what it basically does, one way of doing it is, one way of doing it is you could see once I go to T2 over here, what I could do, assuming T2 is not all the way up there, it's maybe close to that line, that slope. What I could do is I could increase my slope. So I can increase my slope to say, hey, if I have an external fault with CT saturation, I could deal with it by increasing my slope. So I can go from a slope of 30% to maybe 60% or even 90%. And I will not compromise my protection for internal faults, because for an internal fault, my trajectory is different. So for an internal, this is again an external fault. So for an internal fault, I'm going to see an increase in differential and an increase in restraint. And in this case, I know that it's an internal fault. I don't need to check for CT saturation. So we have a CT saturation algorithm that detects CT saturation and applies a directional algorithm to it to supervise the differential if there is a CT saturation issue. So we have two regions of the curve we refer to as usually slope 1 and slope 2. Slope 2 is where we're going to have large currents, and slope 1 is where we're going to have low currents. This could be possible to DC offset, whereas in the region 2, that's where I'm going to actually have where I'm going to strike my fault. It's either with external fault with high CT saturation or internal fault. So I can easily detect CT saturation in region 2 because I have a lot of fault current, and I know, and I could see the saturation effect. I could see the trajectory of the slope of the point going from T0, T1 to T2 as previously shown. In region 1, because my CT saturation might not be a whole lot, that might be very small depending on the DC offset, it's very difficult to detect saturation. So what I'm going to do, in addition to saturation, I'm going to look at something what we call a directional flag. And the directional flag is basically, again, going back to Kirchhoff's current law, is if it's an external fault, current in equals current out. That means that there's the current, at least one current should be about 180 degrees out from the other current, meaning current in and current out. And then I'm going to also set a saturation flag. So depending where I am in the region, I'm going to use these two flags. So in this case, if I go out here for a external fault with CT saturation, I'm going to set my saturation flag because I've seen that trajectory. Once I've set my saturation flag, I'm going to say, hey, CT saturation is detected. I should also verify that it's in the proper direction before I operate. And if it's an external fault, it should not operate because my direction flag that I showed in the previous slide will be 0. So it should not operate. However, if I'm in the internal, if I have an internal fault, then all my currents are going to be about in phase with each other. And I should set my directional flag, but then my saturation flag is 0 because remember, I went straight up like this. So then I'm going to then basically say, hey, I'm going to trip without any delay there. And if I go further up within the region 2, I know I have a internal fault without CT saturation. I don't need to check the saturation or directional flag. I can operate very quickly. So in conclusion, we talked about is the dual slope breakpoint characteristic for the low impedance. We talked about CT saturation principles, the dual protection principle, meaning region 1, region 2 of the curve. We talked about typical operation time, very fast. Stability for external faults, whether you use low impedance or high impedance, differential protection. And a couple of questions here I'd like to answer before we close. Can potential currents in the shield wire of a cable affect this scheme? I don't think, no, I don't think so. When we're talking about is high levels of fault current, so our fault currents will be much above whatever capacitive discharge or EMF interference we see in any type of unshielded cable. I think, and most of the time CT cables are unshielded. More where you're going to run into this issue is for if you go long runs, obviously longer runs, and you have low currents. But it's more shielded issues come in not so much for the CT currents, but for the trip signal. Depending if you're running a trip signal to the breaker and it's a long distance, you could have capacitive discharge into that cable. And if it's not shielded properly, you could have discharge into that circuit and cause an operation of whether it's a breaker failure initiate, an artery closing relay, because they're usually high impedance. However, in most of our relays, we've released an input card to deal with that issue, and it's called an active impedance card. So what it does is, one of the ways we typically design in our circuit to deal with this issue, we put auxiliary relays, right? You put lockout relays, auxiliary relays, because they require more energy to operate. So any type of capacitive discharge, any type of interference is not going to cause the auxiliary relay to operate. So basically what we've done, we've taken an auxiliary relay and we've put it into the microprocessor relay, in so to speak. So we've put a low burden active impedance in the relay, and it's available in all UR relays, but you have to ask for it specifically for it to come with the relay. So if that's something that you're interested in, we can talk about that. Another question we had was high impedance protection. Where do I apply it? What voltage level does it matter? It really doesn't matter, right? Or any type of differential protection, right? It doesn't matter what voltage level. It's how important is that bus to your process, right? Do you really want that fault current to linger on for that coordination time delay if you don't have a bus protection on it. If you could deal with that, if there's stability issue, okay to deal with that, or if you're okay with dealing with tripping out your plant for a stability issue. Arc flash, if you concerned about arc flash, we should all be concerned about arc flash because it's a safety issue. If I don't need to worry about arc flash, I don't need to implement a bus differential. But if I'm talking about arc flash, then so it all depends. It doesn't matter really the voltage level. It matters of how important it is to your process, that bus. What are you looking for? Are you looking to save an arc flash because of the dangerous levels of arc flash? So it all depends. There's no simple answer to say it shouldn't be applied at 480 volts, which is typically not at 480 volts. They're economics, right? Too, it's an expensive scheme. So 480 volt, there are more economical solutions like using an arc flash relay with a light sensor might be a more economical solutions than applying a bus differential relay. So it depends. The other question we had was for renewable schemes, whether it's PV or wind or whatever, renewable schemes. Can this be implemented? Yes, it can be implemented. As I said, it really doesn't matter. It's depending on what you need to accomplish. And the other question was, can we parallel CTs for the low impedance scheme? We don't recommend paralleling CTs for the low impedance scheme, but there's always a caveat or an exception, except for very specific situations. And those specific situation is if you have a radial feed, if you have two feeders that are radial, meaning that if there's a fault, only one of those CTs are going to see fault current, then possibly, yes, you could parallel those CTs because you'll only see fault current on one of those CTs. The thing with paralleling CTs, when both CTs are contributing to the fault current, there could be issues in the CT circuit, saturation, transient issues. And I've seen a lot of misoperations because of people paralleling CTs into differential protection. Except, as I said, you might think about doing, even then it's kind of iffy that if you have two radial feeds, then and only one of them is gonna, for any fault in the system, only one of them is going to see fault circuit current, then it's not ideal, but it's okay to parallel the CTs. But not to say people don't do it. That's been done for a long time because like when we talked about pilot wires, relays, HCB relays back when we first were starting using line differential, the CTs were paralleled. And when we upgrade them to microprocessor relay because we didn't want to mess with the circuit, we still have them paralleled. But as I said, I've seen a lot of misoperation because of that. But those are mostly when you have sources on both CTs. If you don't have sources on either one of those CTs, only one of them is going to subject to fault current, then you might be okay with paralleling the CTs. Did I miss any questions there, Mike? I'm not seeing the questions properly here, sorry.
You might comment on, there was a good question I'm glad somebody raised, and the question reads the equivalent of, can arc flash protection be used in lieu of bus differential protection, or are the two distinctly different or mutually exclusive?
So arc flash is there for a specific reason, and that is to reduce any arc flash energy. And that arc flash energy does not necessarily have to come from a bus fault. It can come from a breaker fault too, right? The switchgear fault. It doesn't necessarily have to be in the bus. So yeah, but with a bus differential, if you have the CTs on the feeder side, then it can also incorporate the breaker as part of its protection scheme, and it will trip for any type of event that an arc flash relay would trip for. So again, it all depends, depending where you have the CTs, but for all intensive purposes, they are kind of doing the same thing in terms of arc flash. They are going to reduce the arc flash energy. So if you have an arc flash relay, you are going to trip the bus for an arc flash event. If you have a bus relay, you are going to trip the bus for an arc flash event.
Can I throw in my 2 cents?
Any other question that I missed?
Mike, can you hear
Yes,
me?
John. Very
throw in my
low,
2
but go ahead.
Let me throw in my 2 cents. For those that are all confused, a lot of systems today were going with low impedance bus differential over high impedance bus differential. And I'll give you 2 quick cases. First is I've got a customer in a paper mill, and they had a high bus differential scheme. Well, everything was fine, but one day it tripped. Making a long story short, turned out when the system was set up, one of the CTs was wired backwards. And unfortunately, in a high bus differential scheme, all the CTs are paralleled.
Right.
So
troubleshooting is very, if impossible with a bus scheme without disconnecting CTs.
Exactly. It's very difficult on high impedance bus differential to troubleshoot it. Plus, CTs have to be the same. The beauty of low bus differential is all the CTs come in individually, so you can see exactly what's going on. The other application we've had on low bus differential is on a retrofit application. A customer needed to reduce his arc flash incident energy, and it was existing equipment. We actually took all the existing CTs from, in this case, motor protection relays, and just seriesed them right through the relays for the motor protection into a bus differential relay. And we actually were able to add bus differential relays system without having to go back and retrofit and add dedicated CTs. And the beauty of that is these new relays
I refer to as we can have promiscuous use of the CTs.
Correct. And the beauty of this low bus differential is I can actually have up to 24 different sources. So like one of the questions came in, do I need to parallel CTs? With GE Multilin being able to have 24 separate sources, you probably can cover everything you need.
I think the parallel comes into mostly sometimes as retrofitting. Can I really run that CT connection? And I might have like 2 pieces of switchgear right next to each other, and I might need to run, cabling to a control room somewhere. Do I really want to run 2 sets of CT cabling, or can I get away with running 1? So, yeah, as I said, I don't really recommend paralleling CTs unless you look at it very carefully. And going back to your point, yes, if I was doing any type of bus protection on a greenfield project, definitely I would go with a low impedance differential. And most utilities have gone that way. Anytime they're doing any type of new installation or new work, they will go to low impedance scheme. High impedance schemes are still out there. They're still specified and they're still out there. And mostly what I see in North America for high impedance are for legacy schemes. So upgrading a legacy high impedance scheme, they might not want to touch the CTs. But most of the newer projects, but in other parts of the world, people are still specifying high impedance as for greenfield even.
I think they just don't know the difference. It's so much more.
Yeah, it could be that, or it could be, yeah, they're just used to that, and people are creatures of habit sometimes too. So yeah. Yeah, I don't see any other questions that I think I need to address here. As Mike said, there's some questions on the material. It's available in the handouts. In our manuals, application guides, we have on our website, ggridsolution.com. If you go to B90, B30 relay, we should have some application guides. In the manual, it goes through some, how do you calculate those differential settings and stuff. Unfortunately, we've just not enough time in this type of environment to be able to go into that detail. Somebody asks about transformer differential. Transformer differential is basically bus differential, but the additional thing that we need to take care of is the winding ratio of the transformer. So we need to do compensating for the winding ratio of the transformer, and we need to consider transformer inrush. So when we do energize a transformer, there's a transient inrush into the transformer, and this is the one case where Kirchhoff law doesn't apply. Current in for inrush condition does not equal current out. It's all current in for inrush. So that can affect, obviously, that can affect the differential because now it's seeing a differential current and it could trip for transformer inrush. So we need to take care of that, and we do that by having an inrush restraint algorithm.
Mike, we actually got asked for a separate presentation on transformer protection.
Okay,
So
okay, good.
I think that'd be a great topic.
Yes. Somebody asked for an email address. You could either contact Mike or anybody from L3 to get my email, but it's also included in that handout that's there.
And a copy of this presentation will be on our website, hopefully later this afternoon.
Okay, unless you guys see any other question that I've missed, we can conclude the presentation. Thanks everybody for your time today. I know we're all in challenging times. Hope everybody's staying safe and following our local guidances from our local governments and continue to stay safe.
Thanks, Mike.
Thank you.